Hi, I'm Kamlenya Bacha, and this talk is a short talk on CertRL, which is joint work with Avi Shinar, Barry Traeger, Vasily Pestun, and Nathan Fulton. For a quick overview of what CertRL contains, we have a formalization of Markov decision processes, long-term values, optimal value functions, and Bellman operators. And we also have a formal proof of convergence of the value iteration and policy iteration algorithms for Markov decision processes in the case of stage 3 policies. We also have a finite time analog of the fact that the optimal value function, and we also have a finite time analog that the optimal value function satisfies the Bellman equation. In this talk, I will explain the formalization techniques which we used for our formalization work, and the details will be given in the long talk and also in the preprint. This is a typical reinforcement learning loop. It consists of an agent and an environment. The agent performs certain actions, and the environment responds by giving the agent a certain reward, and it will transferring the agent to a new state, at which point the loop continues. The goal of a reinforcement learning algorithm is to find a policy mapping which maps states to actions at each instant in time, so that the agent's long-term reward, which is simply the discounted sum of each of the individual reward at each time instant, is maximized. Another important thing which I wanted to say is that the transitions of the agent are stochastic. If an agent at a state S performs an action A, then the next state can only be specified up to a probability. In other words, given a state S and an action A, the output is a probability measure on the states S, and that probability measure may or may not be deterministic. The primary correctness property for any reinforcement learning algorithm is convergence. We would like to say that the algorithm converges to a policy that optimizes for the long-term value. Value and policy iteration algorithms are two such algorithms. They are canonical because they are taught in reinforcement learning 101. And the convergence proofs depend on Markov decision processes and the one-hour fixed point theorem. And these are typical of convergence proofs of most reinforcement learning algorithms. And so they made a good first target for us to formalize. So as I said, the convergence proofs depend on Markov decision processes and the one-hour fixed point theorem, and our two design decisions were motivated to those two areas. So we use the Giri monad to capture the transition structure of a Markov decision process, and we use the metric co-induction principle to reason about fixed points of contractor maps. Excuse me. So let me explain both of these in turn. The Giri monad, for any reinforcement learning algorithm, we are interested in the behavior of an agent n steps from where it starts out. And because the transitions are stochastic, we would like to compose probabilities in order, if we want to make any statement about the long-term behavior of the agent. So classically, this is achieved by a state transition matrix whose powers are then used to calculate the probability of an agent. But formalizing this directly would require us to formalize matrices and matrix multiplication, which could be quite tedious. And so our key idea to replace matrices and matrix multiplication was to introduce the Giri monad and to use the class decomposition of the Giri monad to replace matrices. This is done because the class decomposition of the Giri monad recovers the Chapman-Kolmogorov formula. If P of A stands for the type of all discrete probability measures on type A, then we can equip P with two operations, the bind and the return, which make the triple P bind and ret into a monad called the Giri monad. And if you're given two Kleisli arrows of the Giri monad, that is arrows from A to P of B and B to P of C, then Kleisli composition simply puts these together to return an arrow from A to P of C. Now, probabilistically, if we expand out the definition of the Kleisli composite of F and G, we recover equation 3. Now, if you focus only on the summand of equation 3, it's Fxp multiplied by GBC. I read that as the probability of starting out at X, going and ending up at C through a specific intermediate state P. If we sum over all possible intermediate states, then we get the total probability of starting out at X and ending up at C. Now, this is exactly the Chapman-Kolmogorov formula. And so we've recovered this formula via Kleist decomposition. Now, in a Markov decision process, as I said, if we undertake a particular policy, that means if we perform a certain action at a given state, then we get back a probability measure on states. And if we perform another action, then we get another probability measure, and we would like to compose those probability measures. And say if we want to do that k times, we simply take the k-fold Kleist iterate of one single transition map to recover the entire transition structure after k steps of the agent. And this is how we use the GD monad in our formalization. Another technique which we used was the metric co-induction principle. If you are familiar with the value iteration algorithm, you will know that it proceeds by proving that the optimal value function is a fixed point of a contractive operator, and hence it can be approximated to any degree by the proof technique by the computational content of the Banach fixed point theorem. This is what the Banach fixed point theorem says. If X is a complete metric space with a closed non-empty subset, and if F is a contractive operator which preserves the subset, and then the fixed point of F lies inside the subset, and it can be approximated by repeated iterations of an initial point starting from any initial point of this in the subset. Now we can restate this as the following proof rule, which I read as saying that if phi is a closed non-empty subset of a complete metric space X, which is preserved by a contraction F, then the fixed point of F also lies in the subset. Now this, stated this way, this proof rule is called metric co-induction, which was described by Dexter-Posen in a couple of papers. This proof rule is important because it helps us streamline and simplify proofs of theorems of streams and stochastic processes. Typically, whenever we want to prove that a particular property holds up a limit, we would need to resort to low-level epsilon delta arguments. But metric co-induction helps us sweep all of those arguments under the rug because the work has already been done by the proof of the fixed point theorem. And so our reasoning now is transferred one level up, where we can reason algebraically and our proofs become much simpler. For our use case, we use a version of metric co-induction called contraction co-induction, which is named so by the paper of Faze, Hansen, and Moss, whose paper we formalized for our work. Contraction co-induction simply allows us to reason about order statements concerning fixed points of contractive maps. So contraction co-induction says that if F is a monotone map, or if F is a contractive monotone operator, in other words, if F preserves sets of this form, then if F is less than or equal to X, then that implies the fixed point of F is also less than or equal to X, and also the dual statement. Now, as proof of how contraction co-induction helps us simplify proofs, on this slide you see an English version and a Coq version of the same proof. On the left-hand side, we have the English version. On the right-hand side, we have the Coq version. You can, comparing the lengths, we see that they're pretty much the same size, but more importantly, the reasoning performs at the same level of abstraction. So even qualitatively, both of these proofs are saying the same thing. So this goes to show that proofs using this proof rule are formalizations using this proof rule rather are very pleasant to undertake. On this slide, I have a proof from a textbook of the policy improvement theorem. And I don't want to go through all of the details, but roughly you can see that there is an infinite sum being expanded. And then there's a property that each partial sum of this infinite series satisfies the property A less than or equal to B. And since the partial sums converge to the series, the property A less than or equal to B also holds up the limit. Now, instead of doing this way, if we use contraction co-induction, we can deduce that the fixed point, which is V pi, satisfies the property as soon as the initial conditions are satisfied. And so we would not have to perform all of the intermediate steps because the work, as I said, has already been done once in the proof of the fixed point theorem. So that goes to show how contraction co-induction helps us simplify proofs. Now, as conclusions, we've proved convergence of classical value and policy iteration algorithms in COC. We've also computed optimal value functions for a possibly non-stationary policy for a finite horizon MPP. We've used the Giri monad and contraction co-induction to streamline and simplify proofs. And for as future work, we are aiming at stochastic approximation algorithms for model-free reinforcement learning algorithms such as Q-learning. Thank you.